Welcome to Statistics in Excel video number 50. Hey, if you want to download this workbook or the PDF notes, if I got them here, go ahead and go to my YouTube channel, then go to my college website link, and you can download this workbook and PDF notes. Hey, this is chapter 4. We're going to talk about probability. And a lot of this is going to be defining terms. And so I actually am going to start off this first video by looking at handwritten notes. These are just as I would write them on the board. Probability. Here's another note. This is the point at which in this statistics class it gets pretty difficult for most people. For whatever reason, probability seems to give people a trouble. So we're going to go over lots of terms and whatnot. These handwritten notes, unlike earlier chapters, are probably pretty important. So you want to download these and the workbook. Hey, basics of probability. We have probability. What is probability anyway? Hey, probability, chance, likelihood. Those are all synonyms. Those are the similar words for the same thing. Probability means the chance that something will occur in the future. Or, even better, in this textbook, they define it as a numerical measure of the likelihood that event will occur. Now, I like that numerical measure because it is a number. Hey, if we have e to the I, e sub I, as the ith experimental outcome, like rolling a 6, right? I want to see what's the probability of getting a 6 when I roll a die. And this stands for our probability of that, like probability of rolling a 6 is 1/6. Then probability is a number between 0 and 1 inclusive. Always, no matter what, if you see a number that's negative or greater than 1, you immediately say that is not a probability. All right, probability is never known with certainty. It is only an estimate, right? Because we're estimating something into the future. Do you know the future for sure? Well, probably there's a couple things that get pretty close to 1 and 0, right? What's the probability that the sun is going to go out in the next 10 seconds? That's pretty close to 0, so pretty close. Hey, what's the probability that it's going to rain at least one time this year in Seattle? That's probably pretty close to 1. Right? And those are probably pretty certain. But never, the future is never known with certainty. P of whatever the event sub I is only an estimate of an event that may occur in the future. Then we need to define experiment. Hey, like I said, we have nothing but terms to define. What is an experiment? Any activity that has 2 or more possible results and it is uncertain which one will occur. Hey, what about this as an experiment? Toss a coin. You're either going to get what? Head or tail. You drive on a bridge and you're interested in traffic, right? You either get stuck in traffic or you're not stuck. Roll a die. You can get only one of those. Make a product. It's either, if you're interested in whether it's a defect, it's either a defect or it's not a defect. These are called experimental outcomes or sample points. All right, so probability and experimental outcomes. Sample point, that is a synonym for experimental outcomes. And the textbook uses them somewhat interchangeably. One of the experimental outcomes, example, flip one coin. A sample point is the head or it's the tail. Right? A sample point is also an element of the sample space. But what's a sample space? Sample space is just a list of all the possible experimental outcomes or all the sample points. Let's look at 2 examples. Sample space for flipping the coin one time. There it is. S equals, in these little curly brackets separated by a comma, head or tail. But what about sample space for flipping a coin 2 times? Here it is. Oh, you could get a head-head, right? You could get a head-tail. You could get a tail-tail. Oh, and you also could get a tail-head, right? Sometimes when you don't list all of the sample points in this way, you get these 2 mixed up, and then you think, oh, there's really only 3 possibilities. Each one of these is a sample point or one experimental outcome. All of them together, the sample space. Oh, multi-step. That's what this is, a multi-step experiment. It just means an experiment with more than one step. Most experiments experiments are going to have more than one step. Flip a coin 1 time, flip a coin 3 times. Hey, what about drive across the bridge 7 times? Later, we'll try and figure out what the probability of getting stuck in traffic all 7 days, for example. Oops, I keep clicking the wrong thing. I want to go to next page in these PDFs. Now, tree diagram, very important. Let's just look down here. Very important because why? When you have multi-step experiments, it is just plain hard to list all of the sample points in the sample space. And so this is a trick for doing it. You start here. Possible outcomes what? When you flip a coin. So our experiment is going to toss coin 3 times. And ultimately, later, we'll like figure out what the probability for getting 2 heads is, for example. Flip, 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 1, 2, 3. We're ultimately, after defining lots more terms, we're interested in things like what's the probability of getting 3 heads. But right now, we just want to list all the sample points. All right, step 1, 2, 3. Each one is a flip. Each one has how many possible outcomes? Well, when you flip a coin 2, right? So you flip a coin, you can get heads or tails. But if you get a heads and you flip it again, right? What's right at that moment when you flip the coin? Still 2 possible outcomes for this one. And you get another head, and then right here, what is it? Oh, this, when you flip it the 3rd time for step 3, still 2 possible outcomes. Now, so you list that for each particular one, and then watch. I've color-coded it right here. So the purple one, that's a unique sequence of outcomes. Tail, tail, tail. The red one, tail, tail, head. And see how we've listed it over here? That's called the sample point. And then we get an orange one, tail, oh, head, tail. Tail, head, tail. And then finally the yellow one, tail, head, head. So then we list it there. We do that for all of them, and we get how many? We can count them on our fingers. 1, 2, 3, 4, 5, 6, 7, 8. Later, it won't be so easy to count how many there are. All right, so there it is. And there is the sample space listed out, all of them. Now, as I said, we can count on our fingers. We get a count of 8, 1, 2, 3, 4, 5, 6, 7, 8. But what if we couldn't count them on our fingers? Let's see if I can get this right. I click right there. All right. Before we look at that formula, this is just an alternative for visualizing multi-step experiments. I listed toss 1, 2, 3. And then I just listed them all. Head, 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 tail. We'll look at this example later. We'll actually do it in Excel. Here's the counting rule for multi-step experiments. Very important. We want to know the total number of experimental outcomes or sample points. How many are there? K is the number of steps. N, number of possible outcomes in step 1. N2, number of possible outcomes in step 2. And here it is. N1 times N2 times blah, 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 until you get to the last N sub K. That's the size of the sample space. Now, we saw an example where they were all the same. Sometimes they're not all the same. If they, so in our example, we had 2 times 2 times 2 equals 8. If they are all the same, then you can simply use this. Same what? The total number of outcomes, right? So this N1, N2, N3, all the way to the last N, each one of them has the same number of outcomes. Then you can just, of course, logically use that formula. 2 raised to the 3rd is 8. All right, here's another example. How about if we roll a die, 2 dice, right? So really, the experiment is we're rolling them at the same time. But conceptually, you're rolling one, and then you're rolling another. So there's really 2 steps. There's 6 possible outcomes on that first die. And the second one, there are 6 possible outcomes. If K is 2, there's 2 steps, and bloop, 36. Now, listing all these can get pretty tricky. And a word of advice, you probably do want to try and list all of the sample points at least a few times in your homework, because it will help, especially when we get to our probability distributions where we're talking about all of them. And it will help because we'll learn the addition rule and the multiplication rule in this chapter. And next chapter, when we do discrete probability distributions, we'll combine those 2 rules. And understanding how to list all the sample points is helpful. Ultimately, when you're doing statistics and probability in your job, you're not going to be listing all the sample points generally. No problem. Here it is. 1 to 6, 1 to 6. The intersection of any one, then it's easy, just like your multiplication table you learned when you were a kid, right? 4, 4, that means a 4, 4. 3, 3, that means a 3, 3. 6, 1, that means a 6, 1. All right. Now, sometimes you want to find the total number of sample points, experimental outcomes, in a slightly different situation. I clicked the wrong one again. But before we get to that, we need to remind ourselves of two things. All of us took algebra, so we know n explanation point doesn't mean that the n is really excited. It means factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. Boom, that's how you do it. If you're doing division, 10 factorial divided by 7 factorial, line them all up and cancel just like you would to reduce a fraction, and you're left with 10 times 9 times 8, 720. Don't forget, 0 factorial is 1. And there's an example. 4 factorial divided by 4 minus 4 factorial is a 0 factorial in the denominator, so you get a 1, and that's equal to 24. In Excel, there's fact, and we'll look at an example of that. The function called fact. All right, one other thing we want to remind ourselves before we get to this alternative method for counting. Do you remember when we did x bar? Oh, that's sample mean. Oh, and mu? That's population mean. What's that little n mean? What's that big N mean? That little n means number in sample. That big N means number in population. N, little n, number of items in population, sample. That's going to be helpful because this author in this textbook, we're going to learn the combination formula and permutation formulas, which you learn in algebra. But they're going to use big N and little n for our variables. Why? Because later when we talk about the central limit theorem, combination formula is very helpful when we're talking about populations and samples. All right, so our goal, what we want to do is find all possible combinations of sample size n from a population with size big N, right? Now, technically, this is the definition of a combination. Now, we want to decipher between combination and permutations. Again, this should be a review from algebra. When you're calculating the total number of combinations, order doesn't matter. So when we get a 1, 2, forget it. We're done with all the 1s and 2s. 1, 2, 1 here. These are both considered the same thing for a combination. So you only count one of them. Order doesn't matter. When we do our permutations, order matters. So 2, 1 is not the same as 1, 2. We actually have to count both of those. All right? So here's our definition of combination. Count total number of experimental outcomes, sample points, when selecting n objects from a set of n objects. Right? So here's our formula, big N factorial divided by little n factorial, and then in parentheses, because we got to do that minus first. Big N minus little n, and then a factorial. Now, the big N is the count of all objects. All objects. And n, objects taken. That's one way to think of it, like the objects taken like a sample size, right? Sample size. Another way to think of this n is items selected. Another way to think of it is, oh yeah, n is a subset from a bigger set, right? And order doesn't matter. That's our formula. I clicked the wrong thing again. And then there's our permutation. That's where order matter. You just leave off that little n factorial right there. There's our formula. Now let's look at a couple examples. We're going to, before we look at the population sample example, I just want to give you a nice, straightforward, easy to understand example for our combination. Here's Che Dawson. He is the basketball coach here at Highline. Che Dawson has a team, and he has 12 total players, and he needs to figure out how many 5-person teams there can be. Well, oh, that's got the wrong notation there. That's little n, and that's big N. All right, so there's a little n equals 12. The big N and little n is 5. We go ahead and do our combinations. 12 factorial divided by 5 factorial, and then in parentheses, 12 minus 5. We go ahead and do all our calculations, all our lovely math, and we get 792. How does Che Dawson do it? How does he pick between all those combinations of teams? Well, luckily he doesn't have to do all this math because in Excel he can just use the combin function, which we will do. Put a 12 there for the size of the big group, and 5 for the size of the subset, and then there you get it. Permutations, here's our next example. This is on page 11 in our PDFs. Same thing, except for when Che decides a team, he has the first letter for these 1, 2, 3, 4, 5 players. But notice JSTCZ. Oh, and he just switches this around. SJ and then TCZ, they're the same as those. But this one is different than this one. That is permutation. 95,040. Oh, my heavens. Luckily, I didn't have to do that math. That's going to be a lot of different teams to pick from. Che must be a genius or something like that to pick from all those. But there you go. There's Perma. We'll see that in Excel in our next video. And that's how you calculate it. Let's go to our next slide. Now, here we have 4 boomerangs. And we would like to find all possible combinations of sample size 2 from a population size 4. Again, later we'll use this in our central limit theorem to prove that some aspects of that are true. We want to select randomly select 2 of 4 to test. Order does not matter. There's our big N, our population size, our N, our sample size. We calculate it and we get 6. Now, in Excel, this is the combin again, and it will ask for a number and a number chosen. The number is the big N. Number chosen is a little n. We'll get 6. Now, we're going to want to list these experimental outcomes, and we'll see how to do that in Excel. But basically, you take the B and you put it with a C, B with an S, B with a D, and then you go down to C. Well, we already did a CB, so then we go C, S, C, D, and we'll do that over in Excel. Now, what if order does matter here? We get 12. Here's our experimental outcomes, all of them, and this gets a little bit more tedious to list, but we'll also do that one when we get over to Excel. Next page, methods of assigning probabilities. 1, 2, 3. Classical method. This means all experimental outcomes are equally likely. Oh, yeah, flipping a coin, rolling a die. So, example for rolling a die, there's 6 equally likely outcomes. 1, if you're trying to get a 1, it's still 1, 6. If you're trying to get a 2, it's still 1, 6. How about getting audited by a district office, right? This office always does, they have 3 million tax returns that they cycle through, and they always do 3,000. This would be classical. You just take the 3,000 divided by that, and you get 1 in 1,000 that you're going to get audited. Next method, relative frequency. Oh, we already did this. Earlier chapters when we were counting how many particular items in a group or a category there were, we then divided that number, that frequency, by the total. And in this method, you use past data to predict the future. Now, example, if your instructor gave out 10 A's out of 100 in the past class, then you could use that past information, 10 divided by 100, and you would get 0.1. That would be using the relative frequency. Now, the law of large numbers, which I have written off to the side here, just says that as the number of trials increases, the relative frequency will approach the true probability. So the more you can. And then there's subjective method. This is when you can't realistically assume that the outcomes are equally likely, and you have little past data. And guess what? This will be called your personal belief. You'll still use the best information you have, but part of this is going to be you kind of just using intuition, and so therefore it's your personal belief. Examples, who will win the Super Bowl? Hey, but wait a second, there's lots of past Super Bowls. Yeah, but there's not the same conditions. There's not the same people on the team, the same coaches, the same weather, all sorts of things. What about a merger between Google and Microsoft? Well, nothing like that has happened. Again, maybe we could find something sort of close and sort of estimate, but that is subjective. All right, next page. Requirements for assigning probabilities. Not too hard, these two things, but oh so important. We already mentioned this one. Any particular probability has to be what? Between 0 and 1 inclusive. And number 2 requirement, when you add up all of the probabilities from your sample space, all experimental outcomes must be equal to what? To 1. Remember, all the way back, so 1, 2. Very important, and we'll see an example of that coming up. Let's go to our next page. An event. We have to define what an event is. An event is a collection of sample points, one or more. So let's look at this experiment. We're going to toss a coin 3 times. Let's say we wanted to calculate the probability that we get 2 heads. So the probability that we get 2 heads. Well, you might be tempted to just go head, head, tail. Oh, there's only one of them. But no way. Look, when we list all of the sample points in our sample space, we see that 1, 2, 3. There are 3 times in the sample space that this occurs. So if you're trying to calculate the probability of getting 2 heads in 3 tosses, you really do have to some way know that there are 3 of them here. Now this is classical probability. Means we have each outcome is equally likely, so each one is 1/8. But if we add these up, we get 0.375. That is the probability of rolling 2 heads in 3 tries. So this event is collecting. We're collecting these sample points up, and those are them. And then you can calculate your probability. Now, let's just look down here because we kind of jumped to a conclusion. We just add these up. But look at this. Probability of an event. The probability of any event is equal to the sum of the probabilities of the sample points in the event. So what is if we're going to roll 2 heads in 3 tries, we have to do whatever our sample space is for this event. There it is. There's 2 heads. There's 2 heads. There are 2 heads. Remember when we did our tree diagram, that was a unique sequence. But each time you get 2 heads. So the probability of 2 heads in 3 tries, boom, you add them up. All right, next page. This probably is self-evident, but S, that's a sample space, right? The probability of S, the sample space, oh yeah, it's always going to be 1. Also, we already mentioned this one, but classical method is when it's used to assign probabilities. All the sample points are equally likely, so that's why you can just say, hey, the number of favorable experimental outcomes. In our case, what we were rolling 2 heads in 3 tries. So there was 3 of them divided by total number of all the experimental outcomes, 8. So that is for classical probability only. All right, next page. Actually, let's go back. I think that's it. Now, we want to go in our next video, we're going to do a bunch of this stuff in Excel and look like at a comprehensive example that'll go over these concepts. And then we'll come back to our PDFs. All right, see you next video.